just as a recap, yesterday we were discussing about CNNs, convolutional neural networks, and just very quickly, if you remember, so we say that convolutional neural networks, you should think about them like some filters that if you are going to take some kind of images, they are going to basically convolve the image, and we talk about things like the kernel size. We talk about something like the number of, let's say, kernels. We talk about padding, and we talk about the strides, right? And also about the pooling thing. So it will be, I think, it will be nice to maybe do a very simple exercise just to see that how this thing works. So I'm coming here. I'm going to the notebook, and the same thing is a Google Colab. You don't need to do this right now. You can do this later. So let me connect. I'm going to use a GPU. Let's see. OK, so I'm in. And now I'm going to upload the data. So I'm coming here. I'm going to come here, and I'm going to say we're in day 2, and this is the data. OK. And it's going to take a little bit because this data is a bit long. But yeah, it's going to be done in like 2 minutes. So let me just explain what we are trying to do here. So what we have is, as we discussed yesterday, we have these camel simulations where, these are, you should think about these like different universes. So for instance, maybe in this universe, we have omega matter to be like 0.3, and sigma 8 is going to be like 0.8. And maybe for this one, we have omega matter to be like 0.4, and sigma 8 like 0.9, OK? And we have like 1,000 different universes. So what we have done is that for each of these universes, we have basically take like a slide here. So you should think about this, like maybe you take like this, like this. You take all the region there, and basically you just project this. You should think this like maybe some kind of weak lensing map, something like that. So our data really looks, we are going to show you later, this is going to look like maybe a cluster here, a halo here, something here. Maybe you have filaments, something like that. So this is an image that is going to come, let's say, from a universe where omega matter is like 0.3, and sigma 8 is like 0.8. Like this is coming from this universe. And now what we're going to try to do is to train a convolutional neural network on this image. We're going to say, OK, try to locate feature, edges, maybe halos, the filaments, such as you are able to predict the value of the cosmological parameters. So another way to formulate this is like we're going to say, let's say for omega matter. So we want to say that omega matter will be a function of our image, right? So this is going to be the image where you have the halo here, here, here. OK? And basically, we're going to train a convolutional neural network to see if we can approximate this function, right? That we don't know this function. This function should be like super complicated. How do you write a function on the image, right? So this is a complicated thing. But we're going to use a convolutional neural network to try to approximate this thing. Yes, so that's a good question. So for every universe, we have, I believe, 15 slices. So we will be using, I think, 800 universes to train. We're going to use 100 universes to validate. And we're going to use another 100 to test. But for instance, for this 100, in reality, the number of mass that we have is like 100 times 15, right? So 1,500. Is that clear? Any question regarding the setup? We are just basically trying to do a simplified version of what people call likelihood-free inference, simulation-based inference. If someone gives you like the image, we don't need to compute summary statistics. We can just try to extract all the information from the image there. Please. Very good question, exactly. So for all these slices, all these slices are going to look different, right? In one of them is going to look like this, but with the same value of the parameters, there will be another one maybe looking like this, okay? So it's going to be different images, but all of them have the same parameters. They are from the same universe. Very good question. Other questions? Okay, so that's basically the setup. So I think this finishes uploading this. So yeah, let's do the same thing. This is just loading the libraries. Basically, we load like PyTorch. This is just to say if there is like GPUs. And we say that CUDA is available, so we have GPUs. And for this, if you run the notebook using CPUs, you will really see why we need GPUs, right? It's going to be way much slower using this. So with this, we are just loading the data. We are just going to say this file with images, we are loading it, and we are loading the value of the cosmological parameters. And what this is telling us is that, all our data has 15,000 images. So remember, this is because all our simulations are 1,000. We have 1,500 maps per simulation, so there are 15,000 maps. And then, for the value of the cosmological parameters, it's telling us that, we have a file with 15,000 cosmological parameters. And in this case, we only have two parameters, omega matter and sigma e. There is no astrophysical parameters. I think even in this simulation, I vary the astrophysical parameters, but for some reason, I didn't put the astrophysics. It doesn't really matter. So the 64, very good question, yeah, Rogerio. So I forgot about this. So this is like the number of pixels in the image. So this is an image with 64 by 64. So we have 64 pixel by 64 pixel. So the image is very small. You will see later it's a bit crappy, but otherwise we will not be able to, I think, to train here today.
How all the images were compressed into a single file?
I just put all of them together. So you will see, yeah, you can see it's really in this file there is this matrix with 15,000 times 64, 64. So it's really that. It's a matrix with the data. All right, so I'm loading this. Here I'm just printing some information. So I'm taking, for instance, the first map. And I'm saying, what are the dimensions? So the dimensions are 64 by 64. And I'm just plotting the maximum and the minimum. So this is the values. And I'm plotting the value of the cosmological parameters. So for this, omega matter is 0.3, and sigma e is almost 1. So let's plot one image. So this is how one of these images look like. So again, it looks a little bit crappy, but this is an image that is coming from CAMOR simulation, so really state-of-the-art hydrodynamical simulation. The physical size, as you can see, is 25 megaparsec. So even if the image looks a bit crappy, this is really like exploring like very, very small scales, right? So let's do the calculation. So, if this is our image, and this is 25 megaparsec, and I have like, let's say, 64, blah, blah, blah. So every let's say, this thing will be like 25 over 64, which I don't know how much is this. But it should be around maybe 0.1, something like that. Maybe someone can, yeah. It doesn't matter, but it should be like this, megaparsec over h. So, these are really small scales. We're talking about, images that go down to 100 kiloparsec, right? These are scales that we're not usually doing cosmological analysis on such a small scales. And, the maximum scale that we have is 25. So for instance, if we think about the fundamental frequency, so the fundamental frequency, KF, will be 2 pi over L. So basically, let's say, so this is roughly 6/25. And this is, again, I'm super bad with math. So this should be like 1/4 roughly. And this is like 0.25, 0.3. So this is 0.3 h/megaparsec. So the minimum K that we have in this image is 0.3, which is already where perturbation theory breaks, right? So we're talking about a system that is incredibly nonlinear, that I don't think you can really analyze with perturbation theory this image. So let's try to see if with machine learning we can do this. Any question regarding this? Okay. So for this thing, the same thing as yesterday, we need to define the hyperparameters. So we're going to say that our bat size, that if you remember, we need this to compute the derivatives of the loss function with respect to the parameters. We're going to take batches of 32. The learning rate, how much we are updating the weights is set to 10 to the minus 4. Dropout, how many neurons we let's say cancel 0.5. So 50% of the neurons we are going to put to 0. And then the number of epochs and nothing else. Okay, so I'm going to execute this. This is basically the way that we create the data set. You can go into detail about this, but we are reading the maps, we are calculating the dimensions, we are normalizing the thing, and we are splitting in training, validation, and testing. So really nothing fancy here, and I don't think it's worth maybe going into more detail about this. So I'm just executing this, creating the data set. So now it's done. And now this is our architecture, right? So let's discuss this in more detail. So this is really the way that it works. So let's try to break this down. I'm gonna erase this thing. So we are starting with the image. Save here. So let's say this. Okay. And the first thing that we do is to pass this to this thing that is called self C1. So if you go to self C1, you can see that here we are defining a convolutional layer where we have a kernel size of 4x4. So remember, this is an image that has 64 by 64, and we are going to convolve this with a kernel that is 4x4, like this. So 4x4. So we're going to convolve this. Yes, right now with this we are only doing like this scalar, like the kernel convolution. We are putting this into the image. The same thing as, yeah. Not really. So we will need to use the formula. I don't have it here, but the formula that we saw, like size minus kernel plus padding, all these things.
So these kernel then will change the minimal scale.
Yes. It's going to create like a new image that I think is going to be smaller than this. But at this point, this is not. It's not. Let's say. It's going to be an image, but it's going to be something already more abstract, right? It's something that, what is this? I think the way to interpret this is that, this kernel is going to extract information by blocks that are 4x4. So 4x4 is going to be like, maybe from scales that are a maximum 0.4 by 0.4. On larger scales than this, it's not going to be able to extract information right now. Belen. Your question is why 4x4 or? Oh, yeah. Well, I mean, once you train this, you can take a look at the kernels, try to see how it looks like. I have done this in the past. I don't understand anything, right? This is like...
So the kernel is a hyperparameter?
Yeah, so every value of the kernel is a weight, and this is really what you optimize. So, the kernel is free, and the network will learn the optimal kernel, let's say. Yeah, and so, some people has been doing is like, for interpretability, let's look at the weights at the kernel. Again, it looks horrible. We can look at this later. It's like, this is when you go to the psychiatrics, no? And it's like, what do you see in this image, right? So I have never been able to understand this. But yeah, please. Yes, exactly. So everything here is a hyperparameter. Let's say the kernel size, the number of strides, the padding, all these things is a hyperparameter. That's why I'm hard coding it. And in principle, you should vary these things. You don't know how much time I spend varying these things. I will say that good rule of thumb these days is that don't really do these things. There are architectures that we know work very well. Like which one? Maybe someone can help me with this. I mean, there are classical architecture. What is? Some of you know this thing. Like, I mean, things like AlexNet. I think there are something more sophisticated than this. Say again? No, not a unit. Anyways, if you ask ChatGPT, he will tell you there are some classical models. All right, so we are just basically doing this first operation. So this is the thing that we are doing until here, okay? So the next thing that we do is this B1. So B1 is just a batch norm layer. So it's a little bit technical, this thing, but basically it's like, when we input things to the network, usually we normalize things, right? Because we know that this is going to help us. But once you do this operation, the things might not be normalized, It might be completely very far away. Yeah, Roger.
So if I understand correctly, you don't even know the number of nodes in the input parameters to start with, because this depends on the kernel, right?
You don't know the number of points? What do you mean?
So the number of nodes for input.
The number of nodes per input.
No, for the input. So what are we inputting in the network, right? Inputting the image.
Yes.
It's actually inputting not the image, but the convoluted image. So you don't know what is the number of nodes that you need in the input layer, because you don't know what is the convolution ratio. Is that correct?
Oh, I see what you mean. So the numbers inside these kernels are random.
No, the numbers, but the dimension.
The dimension is something that you need to design. So for instance, if you put here 5 by 5, this might not work, right? Because then it's going to be, yeah. So,
Okay, but the dimensions.
yeah, you need to really play with these things. Yeah. Any other question? So this batch norm is basically something that is going to take the image and it's going to kind of normalize again, just to be normalized. We don't have to go into details about this. Okay, so this is everything until here. And then the last thing that we do is our typical thing, like a nonlinear activation function. So it's basically like our typical, let's say, ReLU, and we do like this. So that's the very first layer. In the second one, and that time, yes, but let me explain this, Roger. Yeah, that's a good question. So even if we have 15 slices, we train the model only one by one. So in reality, you only have one to start with. That's a good question, yeah. And I'm trying to see where this is it. Okay, and this is another important thing. So, we only input an image. This is what we have here, 1. But the number of kernels that we use is this hidden, which is another hyperparameter. So in reality, we are not having a single kernel here. We have like, this hidden number of them. This will be 4 by 4. And same dimension, exactly. But the weights will be different across kernels. Okay? So typically, I don't know, you will be maybe 10 different kernels or 15, something like that. And you basically try to learn what is the optimal kernel. And again, this looks like a little bit of Lego block. It's like, should I put first the activation? Should I put the convolution? So you should just remember, if you use this, that the way to do this for CNN is called CBA. Convolutional layer, batch norm, and activation. CBA, 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 always. CBA. And then, basically we repeat the same thing. So now, we take the result of this. So now this thing is going to be, let's say, another image that I don't remember what dimension will be, but let's say this is like 32 by 32, okay? And now we will not have a single image. We will have, maybe 15, like the number of kernels. And then we repeat this again, right? So now we take these images, we convolve with new kernels. So for the C2, these are going to be also kernel size of 4. So again, this is going to be 4 by 4. And you will have many of them. And then you will have another activation function, right? So you do this several times. That's basically everything that is written here. And then, at some point, your image will be small enough. So, maybe after doing all these things, your image is only going to be, let's say, 8 by 8. Okay? So at that point, 8 by 8 is only like 64. This is maybe small enough, so we can already train a fully connected layer on this. So what we do is, like, we take this thing and basically, let's say we flatten this. So let's say this is like 1, 2, 3, 4, 5, 6, blah, blah, blah. So we will take this and put this in a vector. And this is 1, 2, 3, 4, like that. It's like at this point, we just flatten the matrix. So that's what this thing here is doing, this view. It's a super weird notation, but. And then, we have a fully connected layer at the very end. Yeah.
So you're doing this in order, seems to me, in order to be computationally treatable, that you can get down to 8 by 8.
Yep.
Now, in principle, this is a matter of principle, right? You have an infinite computer power, you could flatten the whole image, right?
Yep.
So my question is, have you tried to see if there's any difference if you flatten the whole image, or does it lose information?
With this, you lose information.
Any difference in the structure of the parameters?
Yeah, I mean, you can flatten the whole image and put into fully connected layer, and in principle, that should work better. But in practice, it's so hard to train that no one really does this. No one does this.
So it's not a matter of principle, it's a matter of...
Exactly, it's a practical thing. It's a practical thing. It's like, I mean, why in the simulation you have a...
Even if you had infinite computer power and you do it, you still wouldn't get a much better result.
Let me see if I understand. If you have infinite computing power and you are able to flatten this, I think that should work better than the CNN. Also with infinite amount of data. I think that's the case. Because when you use this, you are also using assumption, as we were discussing yesterday. You have some inductive biases that I think with fully connected layers you don't do.
Thinking about what you said, I always try to think that the CNN maybe be just a way for you to clean up your data. So you're extracting relevant features of your image, and you're only training your model with this relevant feature. So you could like simply flatten the original image, but I don't know, it's computationally better for you just to clean up.
We have some noise in the original image.
Yeah.
Yep.
Maybe overfitting, but again, it's still just...
Yeah, no, but that's a good question, yeah. Any other question? Okay, so the very last thing that we do is that given this, we pass into a fully connected layer, okay? So we take this, and I should have put this like this, not like that, but, and then at the end, you just have here, let's say, omega matter, okay? So that's really our network. You take the image, you pass into the convolutional layers, kernels, nonlinear activation function, you repeat this several times, you are decreasing the dimensionality, At some point, it's small enough, you flatten it, and you pass into fully connected layers. And sigma 8, yeah, exactly. You can do several parameters, not only one. Yep. Okay. So that's our architecture, really. This is really the most important thing. And okay, so that's it. Then we are going to define our loss function, the same as yesterday, the mean square error, and the optimizer, Adam. I don't know if you about this, but there was recently, there was NeurIPS, this big machine learning conference, and it goes in all how it's called, all social media, because apparently one reviewer, who in this case I'm pretty sure it has to be a human, was asking is like, I mean, the authors talk about Adam, but it does not appear as an author or something like that. And it's like, who is this Adam? And it was like, I mean, like a joke, because, I mean, Adam is a very well-known optimizer, right? So, this is one of the things where probably an LLM will not have made that comment. But if you Google this, like, who is Adam, something like that in Google, you will see a lot of fun about this. All right, so let's train. So, the same thing as yesterday, we do a loop over the number of epochs. We do a loop over the number of batches for every epoch. And here is like, we are taking the maps, we are taking the parameters, we are computing the loss function, and then all the magic happen here, where we are updating the weights, and we are doing that. Okay, so the same thing for this, validation, the same thing. So let's do it. And now this is gonna run, I think, fast, because we are using GPUs. And you see, this is epoch 0, this is the training loss, this is the validation loss. And you can see that it's going down. So remember, initially these things learn quickly, but at some point probably it's gonna plateau. And remember what we are doing here, we're taking the images, we are basically trying to learn optimal kernels to extract the maximum amount of information from the images, basically to infer the value of the cosmological parameters. We are not using summary statistics. Let's say the network is learning the summary statistics for us. Let's say the optimal. Again, I don't want to make claims because people study this in detail, but a naive way to think about this is like the network is learning the optimal summary statistics. So it's gonna train. It should take only like maybe 2 or 3 minutes. I think we put how many epochs? I think 100 maybe, 100 epochs. So it should be done quickly. And every time my validation loss is the lowest, then I save the model. I'm basically saving the weights. I don't want to save the weight, for instance, for this model. Let's say for this one. Because this one has a validation loss that is higher than the lowest validation loss. So I always want to keep with the best model, and the best model is defined as the model with the lowest validation error. Okay, so it's gonna take just maybe 1 more minute. So once this is trained, what we're gonna do is to test the model. So the same thing as before, we're gonna make a loop over all the maps in the test set. And yeah, we're reading the maps, we're reading the parameters, we're inputting the maps into the model that is already trained. The model has never seen these maps. And then we're gonna save like the true value of the parameters and the predicted value of the parameters. And then what is, here we're just denormalizing the thing. So really nothing in particular. So let's wait for the training to finish. Yes, please. That's a very good question. So the answer is yes. You can do this in 3D, 4D, 5D, as long as it's a regular grid, or even if it's if it's a regular thing, yes, it will work. Of course, training this in 3D, we will be waiting here for until, so we cannot do it, but yeah, you can do this, yeah. Any dimensions in principle. Okay, so let's wait. I remember my days, when I was training this thing and you were, come on, because you don't know even if it's gonna work, right? You train this thing and it's like, no, it doesn't work. Okay. I need to, change the learning rate. This super boring when. Okay, so it finished. It took 200 seconds. Okay, very good. So let's test the model. Okay, this should be much faster. Okay, and now here what we are basically plotting is, like the true versus the predicted. And you can see that so let me explain what these plots are. So every point here is a map from a simulation that the network has never seen. This is omega matter, this is sigma 8, this is the true value, this is the predicted value. So let's think, for instance, at this point. This is a point that is a map, this is a map that is coming from a universe where omega matter is like 0.35, and the predicted value is 0.50, whatever, 55. So you can see that it's far away from the true value, which should be this diagonal line. So, there are some scatter, but overall, you can clearly see that the network has really learned something, right? If you have a universe with low omega matter, it's never predicting to be 0.5. And also, as we saw yesterday, it's not just predicting like a horizontal line. So it has really learned something. And again, we have trained this for 200 seconds. But it shows you, you can have an image super complicated coming from a state-of-the-art hydrodynamical simulations with baryonic effects. And you can do this field level, let's say likelihood, free inference. We're doing regression here, not inference, but yeah. And you see, it works, right? So, just to illustrate again the power of deep learning in this case. Questions? This is basically everything for CNNs. Yeah, please. No, that's a good question. So how can we improve this? This could be an exercise. Maybe it's already there. So I will, for instance, train more. I haven't even plotted the loss function, so I don't know if it's already plateau. But definitely, I think with 200 seconds, you are not doing very well. Yeah, so, I will, for instance, train longer, and I will also vary the hyperparameters. I will maybe play with the learning rate. Maybe I will change the number of kernels, the dropout. Yeah. And you can, in principle, I'm pretty sure you will do better than this. I don't think you will do like 10 times better, but you will do better. More questions? Yes, Belén. Mm-hmm. Mm-hmm. You mean like physically or what? But interpretability in what sense? Like what physically produce this correlation? Yeah, I don't think the network will tell you this, right? Once you have a network trained, you can ask questions to it, right? So for instance, you can take, I don't know, let's say for images, right? Something that we have done. So you have your model trained and say, maybe it's like, where is this information coming from, right? Is this coming from the halos? Is this coming from the voids? Is this coming maybe from the filaments? So, something that you can do is like say, okay, so, let's check if it's coming from halos. So what I'm going to do is like, I'm going to remove the halos, let's say by hand. I'm going to train the model, and let's compare this result, right? If I'm getting the same result, this is going to tell you, the halos were not really important, right? You remove them, nothing changed. Or, maybe with filaments, and remove them filaments. So, you can ask these kind of questions, but still it's not easy, Actually, we have done this. And it was not, I can still not tell you exactly where the information is coming from. Please. Mm-hmm. Mm-hmm. Yep. Yeah, very good question. So here, yeah, again, we are doing regression. So regression means that we are just estimating a number, right? We can do inference. It's not very difficult. You know, there are some experts. You can ask Natalie for this, right? So these days we do this, and you know, we were talking before, right? Simulation-based inference. We do this all the time. You can get this, you can get error bars, you can get the covariance. There is no problem. This is something that is very well understood now. So yeah, you can do, let's say, your traditional NCNC, but at the level of the entire map.
Well understood, but how it reflects the current situation? I mean, if we do like standard algorithms, if we use standard algorithms, how the two errors and the uncertainties that we obtain are compatible with each other?
Yes, very good question. So what I will say is that I don't think with traditional algorithms you can even do at the level of the image, right? I don't think so. You can take a summary statistics from the image, let's say the power spectrum, and then say, okay, so with the power spectrum, I write down my likelihood, I compute my covariance, and I get my posterior. But at the level of the image, how do you do that, right? I mean, what is the covariance of this? You cannot even write down a likelihood for this, right? This is not Gaussian. So you cannot even do this with traditional methods. Yep, absolutely. We're not going to do it, but you can get full posteriors, yeah. Yeah. And I was telling you before that, you know, even these days, you know, we do this thing not even in 2, 3, 5 dimensions. We do this in even millions of dimensions. Sometimes an image is your posterior, you know, with diffusion models. So this is really...
Priors would be the range of parameters that you take.
Exactly. So it's, you know, 0.1 to 0.5, this is what we train in the simulations, yeah. Flat prior in this case, but you can change your prior. Yeah.
What kind of treatment do you have to give this image before training the CNN? Let's say, for instance, if you try to, I don't know, build a classification model for,
Mm-hmm.
I don't know, galaxies, for example. Do you think it's better to remove the noise or do any kind of treatment before using it in the CNN?
Yes. I mean, this is very important, of course. I mean, you know, in general, you need to normalize the data, right? So have a mean 0, standard deviation of 1, roughly. You know, with things like noise and this thing, it depends, right? So if you have a lot of data, in principle, it can learn to marginalize over this, but there is something that you can do to, you know, the network doesn't have to learn this, is always better. But the whole idea of this is that, in principle, you should not even do anything. You just throw everything there, and it can learn from that. Depends the particular case. But more questions? Yeah, Gonzalo. What do you mean by fail? Yeah. Yeah, I mean, there are some points here that are very off, no? Like these ones. What do you mean by in the middle? I see. Yeah, for this we will need to look at the full, maybe the full posterior, or something like that, to see exactly if one is right or the other is not. But what I will say is that, you know, from simulation-based inference, we have these days even techniques where you can really quantify if your full posterior is good or not. So this is, I think, a very well understood problem these days. Any more questions? Okay. So if not, this is really everything that I want to say with CNNs. So my plan is to talk a little bit about transformers. I hate this thing. I don't know why you need to do this. Yes, leave. Okay. thought that I updated this thing. Okay, yeah, here. So, I don't really have slides for today. What I'm going to do is basically follow this, in my opinion, really amazing book, Understanding Deep Learning, and my understanding is that everything here is free. So I'm basically just going to use one of the slices that they have about transformers and LLM, but I'm going to probably also write in the blackboard. So the idea of this is that, tomorrow we're going to develop our own agents. So if you were not impressed by the colloquium today, so we will be creating our first agents, like very simple ones to, basically generate an idea. But once you know this, you can really use these agents for anything. You can write code, can make plots for you, really. In principle, whatever thing that you want. So once I think you create this first agent, you will understand this very well, and you will be able to create other agents. So agents basically use large language models, and that's a little bit what I would like to cover today. And the core of large language model is transformers. So I just want to, and this is something that we discussed the other day, is really state of the art. This is what people in industry, they use for everything, right? CNNs, I'm not sure how much they use them, but transformers is really now like the gold standard, right? So if you want to do something state of the art, transformer is really the way to go. So let me see. I have so many things. We wrote so many papers that, sorry, so where is this? Okay, so let me download this again. Okay. And for this, yeah, I mean, it's probably not even, I mean, I'm going to leave it here, but yeah, it's maybe better if I do this a little bit on the blackboard. So, okay, so what is the motivation? So imagine that we're doing, again, and this is the lecture that it might sound is like, what is Paco doing here, right? This is a school about cosmology, so what are we doing with our lives here? So let's say that we are working in natural language processes, right? So imagine that, we have a task that is translating a sentence from, let's say, English to, I don't know, to Portuguese. So let's say that, I don't know, let's say I have a sentence, so Paco is eating too much. He will pay overweight or something like that. Yes, on the plane or something like that. Okay. So imagine that you have this sentence written in English, and your goal will be to translate this to let's say, Portuguese. Okay. So how will you naively do this, right? So maybe let me know ideas. How will you do this? Anything that come out to your with what? Word by word. Okay, but how? Yes, word by word. Okay, that's a good. Any other suggestion? Try to take them in. Okay. Okay, so let me say. So for instance, I think that maybe the most naive thing that you will say is like, okay, so I'm gonna take every word in my dictionary, okay, and I'm gonna, let's say, represent the word as numbers, right? I mean, we know that computers don't understand letters, so we need to represent this as numbers. So let's say that, I don't know, you represent this word as, I don't know, some vector, let's say, in 6 dimensions, 1, 2, 3, 4, 5, 6, okay? And you have numbers here, so 0.1, 0.3, 0.7, 0.8, whatever, okay? And you say, I'm gonna do this for every single word that I have in my sentence, okay? And now what I'm gonna do is basically, I will have, let's say, maybe some set of neurons. This is maybe gonna be one neuron. So I'm gonna take all this sentence and I'm gonna just flatten it. And this is gonna be like a neuron. So this is gonna represent like Paco. This is gonna represent like is. This is gonna represent like eating, blah, blah, blah. And you will have this. And then here, we can have like a fully connected layer, something like that. And this will be like the Portuguese representation. So Paco, no, I don't know how, está, like this, comendo, okay. Like this, okay? And you will have a representation also, a numerical representation of this, and this is, maybe the naive way that you will do this, okay? So what are the problems of doing this? What do you think is gonna be the problem by doing something like this? Exactly. So if the sentence is large, then it's gonna be really incredibly, another problem that you can imagine about this. Overfitting, in what sense? Yes, yes. Yeah, maybe, but yeah, maybe not exactly what. So exactly. That's another good point. And another problem is that maybe the number of words that we have here is, I don't know, 10, but maybe in Portuguese you have less. Or if you write in German, maybe this is like a single neuron. I'm kidding. So just a kid. I mean, a joke. So yeah, this is in principle like a problem, right? And of course, as you were mentioning, if the sentences are very long, this is going to be basically untractable. So one of the motivations about this, let me come here, is like if we want to do this task, what we want is something like the CNN. So if you remember the CNNs, with the images, if you have like very big images and you flatten the image, this is going to be, impossible, right? You will need like pixels square, like the number of dimensions to the square. So with this, it's going to be the same, right? So what we want is something maybe similar to with CNN, something that, if the sentence is longer or shorter, the number of, let's say, parameters does not vary with that. It's kind of the same idea as having like a kernel, okay? And the other thing is that, we want to take into account the context of the different words. Like, for instance, here, he basically referred to Paco, right? So we if the sentence will be longer, this he might be other things. So we need to really say that, this particular word need to take into account the word of Paco. So we need to say that, this particular, let's say, word need to pay attention to the other word. So these are, some requirements that we would like to have it. And, so now let me introduce basically the self-attention mechanism, which is, again, is basically the core of transformers, and this is like a very important thing. Okay, so let's say that we have, our sentence, and it's a little bit weird that in a school I'm talking about sentences, so if you want, you can talk about, for instance, images, imagine that this is like a weak lensing image, and you have pixels, so every, let's say, word is kind of a pixel, it's basically the same idea. So let's say that every word you represent as some vector, xn, okay? Just let me maybe write like this. So this, you should think of this like this, it's a vector, maybe with 6 dimensions, with 7 dimensions, anything like that. So the first thing that you do is basically to do basically like a linear transformation. So you compute something that is called the value. So the value is just defined as, beta, let me put this right, so beta v from value plus omega v plus xn. So what I'm doing, I'm having just here like a vector with some dimensions. This is a matrix, and this is another vector. So you should think about this like a linear combination, right? I'm just doing like an affine transformation, and I'm going from a vector to another vector. I'm just basically doing a linear transformation. That's everything that I'm doing, you know? So I have a word in some mathematical representation, and I'm just basically changing. I'm doing, let's say, some kind of rotation. Okay? So that's what is called the value. And now, and this is very important, so let me write this correct. So the definition of the self-attention so, we're going to define for every value, for every word, we're going to define like the self-attention of that word. And the definition is basically this. So it's basically the sum over all the words. And this is going to be like A, and this is like XN, and this is like XM, I guess. And this is like BM. Okay? So let's break this down. So, I want to compute the self-attention, let's say, of this word, of he. Okay? So what I'm going to do is basically do a sum over all the words. So, I'm going from Paco is eating too much, blah, blah, blah. So all the words. And I'm going to compute this thing. I'm going to define this later, what this is. And then I'm just going to multiply by the value, by this. Any questions so far? Because this is like very important. Let me maybe define what this function is. Exactly. So you have a vector basically with the same dimensions of the one that you started, and you are just saying, let me for this maybe plug in, because I think maybe the drawing is very good to illustrate this. You are just saying, these are going to be things that are going to be from 0 to 1. And what you are saying is that, you are constructing a vector, maybe the self-attention for he should pay more attention to Paco that maybe should pay to pay. Because you want to take into account, like the importance of every word with respect to Paco. So this is an illustration of this. So for instance, imagine that you only have 3 words, x1, x2, and x3, okay? And you have some mathematical representation of them, like, with 3 numbers in this case. So this will be here, the first 3 neurons here, these are these. Then we do our linear transformation, like this, and we get this B, okay? And now what we're saying is that, the self-attention for the word 1 is going to be a contribution from x3, that in this case is like 0.6. This is going to be like 0.3 and 0.1. So, the word 3 is contributing more to the word 1 than the word 2. Right? You're basically just doing a linear combination where you are giving a weight to every word. And this weight will depend on how important the other words are for that particular one. Please. What do you mean is a function? This A is a function, and I'm going to define in 1 second. Yeah. Okay, so this is, is the same thing, for maybe for the second word, you can also compute the self-attention to the second word, and you get the first word contribute 50%, the word itself only contribute 20%, and the other word contributes 30%.
It's like analyzing the sentence syntactically, like the verb gets conjugated by the subject, and just putting weights to it.
Yeah, I mean, to some extent. I think the way that I like to think about this is that, for instance, he here will probably give more weight to the word Paco than to the word is, because he is maybe doesn't really matter for he, but Paco is very important for he.
Do we decide
Very good question. So the importance is something that you are going to learn, right? So you are going to learn the importance between the different words or the different pixels in the image. It's something that you really learn. Okay, is that clear? So let's define this. Let me do this on the blackboard. It's maybe easier. So we need to define two other things that are called the queries and the keys. So the query is going to be exactly the same thing as before. It's going to be a linear transformation. So it's going to be like, let's say, beta q plus omega q times xn. Okay? So this is called, let me just put it here, the value. This is called the query. And then we have to define the key. So kn will be like beta k, I believe. Yep. Plus omega k xn. And this is going to be the key. Okay, so let's break this down. I haven't done anything. I'm just taking my representation of the word, with numbers. Here I'm doing a linear transformation. It's called the value. I'm doing another linear transformation here. It's called the query. And I'm doing another transformation, linear transformation here, that is called the key. Okay, so really nothing, just a linear transformation. And now let me define the attention. So let me maybe write here. So A of xn, xm. Let me see, because the expression is a bit. So this is basically defined as the exponential of qm transpose qn, okay? And then I'm going to do a sum over, I guess, all the keys. So from n equal to 1 to n of the exponential of key m t qn. Let me just make sure that this is an m, but this is an n that goes from here. So this is like an m prime. Yeah. Okay. So this is just the expression for the attention between two different words. So what we're doing is, we're creating this value, query, and key. Again, these are linear transformation of our word. And basically, we're just computing, like the scalar product between these two vectors. And, the way to understand why this is important, so let me plug it here again. Sorry that I'm going back and forth. Xn is the word number n, and xm is the word number. Exactly. Xm, so this is the attention between the word number n and the word number m. There is no x here. This is q. This is q, which is the key. Sorry, it's a bit. Km. Yeah, sorry, Raul. Okay, so let's break this down. So, these are vectors. Think of these as vectors, right? So if these vectors, for instance, let's put in this situation, if this, the scalar product of two products, this is actually incorrect, is the modulus of them times the cosine, okay? So, if two vectors are very similar, what is going to happen with this product? That is going to be large, right? It's going to be large. if, for instance, the angle between these two vectors is like 90 degrees, this thing is going to be 0. And if the angle is very large, it's going to be even negative. So if this number is, let's say, large, let's say it's 1, it means that, the attention between this word and this word is going to be large. This word is really attending to this one. But if the self-attention between this and this is close to 0, it means that they are not really attending too much to that, let's say, to that word.
Attending in which sense? I mean, just describes that this word does not come after or frequently.
Yeah, you should think about this is like, I want a representation of my words, but I want this representation to take into account that this word really cares about this one. It's very correlated to this one. I really need to take that into account. And I should probably not pay attention to this word, because this doesn't really matter for this. Say again? You mean how many numbers you have? This should depend on the tensor number. I'm not sure if I'm following you. This should depend on the tensor number. I'm not sure if I'm... Yeah, I'm not sure. Maybe we should... You mean these particular numbers? Yeah, this is going to be like embedding, so we're going to talk about this later. So this is your initial embedding, and we're going to later to talk about how we tokenize the numbers. But for the time being, just assume that there is a way to go from the word to some numbers. But this is going to be what is going to call the tokenizer. And I'm going to come back to this. Mm-hmm. Yes, so this is going to be learned. The network is going to learn what is the best way to attend to the other words. Exactly. Yeah. So, okay, so you basically get the idea, right? It's like, this is a way, take into account that the sum of all the attention is going to be equal to 1, right? So if I take my word M and I go over all the words, the sum of all this attention is going to be 1. You can see by definition, right? If I make a sum here, so let's say that the sum of over M of A xn xm is going to be 1, okay? By definition. So let me try to see if with this is enough to define the transformers. Yeah, maybe. So, yeah, so basically, this is probably, maybe a good time to stop. So I'm going to just mention this is really like the transformer architecture. Again, this is very important. It's a completely different architecture than fully connected. Well, I mean that, for instance, convolutional neural networks. So what you have is basically, you have your words. And again, this could be pixels in an image. This could be nodes in a graph. Could be anything. So you have, let's say, words. You initially have some embeddings, some mathematical representation. For each of these words, you will compute the value, the key, the query. Then you will pass this into this self-attention thing that we have just mentioned. So you will basically compute the self-attention for every single word, just given by this formula. This is what this layer here is doing. And in this case, it's going to take into account the correlations between the different words. After this, you are going to get a vector. So you know, this thing here is a vector. And after this, you are going to pass this into a fully connected layer, like a traditional one. And that's it. That's a transformer layer. You know, the really, really key important thing is this self-attention mechanism. Basically, this thing. And again, this really very simple thing is really the, the reason why we are seeing these transformative change. This super simple idea is incredibly powerful. Yes, this self-attention is really what comes out after this self-attention layer. We haven't come to the encoder and decoder. We haven't talked about this. This is just like a transformer layer. I think tomorrow probably we will talk about this. Yeah, we will talk about this. So I think in the very early days, I have to double check. I think the embeddings were in 1,000 dimensions. I think now probably they are even larger, maybe 8,000, something like that. Yeah, I think the models that I use is 2,000, I think, dimensions. Yes, we will see later. I mean, you know, this is kind of like the way that it was developed, right? So that's why I'm explaining with this. But people use transformer these days with images. People use with graphs. It's really now at the core of everything in deep learning. So you can use for everything. I think, Raul, you... Exactly. No, everything in one go. Yeah, everything in one go. So, very important. So, what are our parameters here? If you remember, for CNNs, our parameters were the weights, let's say, in the kernels. Here, the only thing that we need to learn are, you know, these betas, this thing, this thing, this thing, this thing, and these things. And, you know, these are vectors, and these are matrices, right? So, that's really everything that we need to learn. And again, I want to emphasize this. This was incredibly important, and still is incredibly important. And you see how incredibly easy it is, right? But this self-attention is really the origin of ChatGPT and all these things. Why? Because it works very well. I'm not sure if we understand this, but it works incredibly well. Incredibly well. There was a question there, I think. It looks like a pre-processing. Yes. Yeah, that's a good question. So your question is like, why should I put even a fully corrected layer here? Right, that's a good question. I think in practice probably just works better. Yeah, I know. Yeah, I don't know all the details, but I think.
So this is trial and error, right? Just one question. Can you go, for instance, you said there was a linear transformation.
Yep.
Transform is a linear transformation. Then someone tried goes a quadratic thing and doesn't work better, it's the same.
Okay, yeah, so that's very important, Rogerio. So these things are linear transformations, but this thing no, right? This attention is not non-linear. And on top of this, you have the fully connected layer. So a transformer is not linear at all, yeah. Raul. Context independent, what do you mean by that? You know, if you're thinking, for instance, something like I input something into ChatGPT, so in principle, yeah, we will talk tomorrow about this. They use the decoder, so your input, the way that you generate the words is going to attend to your prompt, let's say. So that's kind of the way that you, I'm not sure if this is what you mean. We can talk later. I think this is maybe a good time to stop. Tomorrow, you know, my plan for tomorrow will be to just go a little bit beyond this, just to let you know how large language models are trained very, very briefly. And again, this is something that, you know, maybe you will never in your life touch again. And it's like, why I'm learning this in a cosmology school? But I think for agents and these things, you will, you know, you're going to use them. And this is just, you know, some background that, you know, you might want to come back in the past.
Thank you.
I had a question, but so when I'm writing, the computer predicts in advance what I'm going to write nowadays, right? Is it because of this? Because there's attention to what?
Yep.
Yes.
Yeah,
Is that what's going on?
I mean, yeah, exactly.
Okay.
I mean, the way that ChatGPT works, it predicts the next word, given all the previous words.
Right.
So it's really just that.
Okay.
I mean, of course.
Yeah, no. I mean, it's based on what you wrote previously, but it predicts what you're going to write next. So
the next word, yeah.
And this is because of this mechanism.
Exactly. The self-attention is really the core of all this technology.
Okay.
So as far as I understood, these are the techniques that large language models use to train, in order to train. Therefore, this is all the training processes. So they use the largest amount of word embeddings in this case, and then when we give new text, they use the information that they got from previous training, and that's where the self-attention could be able to generate different words that weren't mentioned before in the input that we give. Okay.
Yes, I mean, yeah, sorry, finish, please.
And I wanted to understand what characterize, since we know that there are for example, if I think of ChatGPT, we have different models inside ChatGPT. So for O or 3O, what differentiate in these transformer stuff and training mechanism one model from the other?
Okay, so two questions. Tomorrow we're going to talk how this is really trained in practice. I haven't talked about how this is trained. You will see tomorrow briefly. For the second thing, what are the differences between the models? I mean, my understanding is that, you know, how much maybe text it has been fed into this, also the fine-tuning.
Okay, so it's not something like inside the mechanism or the linear combination that they use in order to train the model?
No. But I mean, of course, at the end of the day, you know, when you have a model, you have some parameters. Let's say 1 billion parameters, right? So you can train your model with 1 billion. With 1 billion, you will do what you will do with 1 billion, right? If you later have 1 trillion parameters, you will probably do better, right? Your network is much larger. It has much more capacity. So that's also the difference between all these things, right? It's like how many parameters, training set, all these things.
Thank you.
Okay, don't see any more questions, so let's thank Paco.
Thank
again.
you.
Have some rest, people. No, we have to wait. Meet with the coordinators. Yeah, the groups. So the groups meet here. So Abby is September, October.